Okay, we saw last time an example of, we saw the definition of projective transformations, and we saw how a projective transformation could induce rational transformations on affine charts, and we had a specific example. Projective transformations induce rational transformations on affine charts, and we had an example where in P1 a map that took an element U in P1, so of course this would be on an affine chart in P1, so on a normal affine line, where it maps to literally a ratio, so alpha of U plus beta over gamma of U plus delta. And we can certainly have a situation where the bottom here is 0, so U is sent outside the affine chart because it would go to infinity, and that you can also sort of make sense of infinity as an actual point, and then you can have the point of infinity come back in to something inside the affine chart. What we would like to do is to see when we get maps which are strictly rational, and when if sometimes the entirety of the affine chart is fixed, not pointwise, but sent into itself, so nothing goes off to infinity and nothing comes back from infinity. In that case, that we get a particular type of transformation which is not described exactly as a ratio, but is actually an affine transformation. So this is the point of proposition 5.13. Which I'll just write down. So fix an affine chart AN and PN, and let T be a projective transformation such that for any P in AN, T of P is also in AN. So it stabilizes the affine chart. Then, in fact, T induces an affine transformation. Okay, so for the proof, we're going to say that without loss of generality, we may as well assume that we are considering the final affine chart. So that is not going to be specific to our case. One can see by just rotating all the coordinates around. So without loss of generality, we fix our affine chart is going to be equal to the last affine chart, which means that the last coordinate is non-zero, and therefore we can divide by it. So we recall that projective transformations are induced by affine transformations of the n+1 dimensional space that the projective space is coming from. So projective n-dimensional space is equal to the set of lines in affine n+1 dimensional space, and since the lines are sent amongst themselves by invertible transformations, invertible linear transformations, we can represent those by matrices. So let A11 up to n+1, n+1, and I'll assume you can fill in the rest of those, be a matrix representative of T. So consider the point uh, 0, 0, 0, 1, so 1 just at the end. This is in our affine chart because the final coordinate here is non-zero. This is in our affine chart. So by assumption, the image is also in our affine chart. Right, so what is the image? The image is, if I put 0 down to 1 along here, I'm going to just multiply and then pick up the last column. So I'm going to pick up the point A, 1, n+1, all the way down to A, n+1, n+1. So this is in the affine chart. And if it's in the affine chart, then that means that this final coordinate has to be non-zero. So hence an+1, an+1, n+1 is non-zero. And so because the matrix will, if you scale the whole matrix by some factor lambda, it will still send the same lines to the same lines. So we can rescale it and then assume that in fact this last coordinate is just 1. So T can be represented by the following. So we go from B1 to Bn+1, 1, up to B1, n+1, down to the last coordinate being 1. Okay. Right, so now let's assume that that this coordinate is non-zero, and then we'll see that that gives us a contradiction. So assume Bn+1, 1 is not equal to 0. But now the point, if I take minus 1 over Bn+1, 1, all the way down to, so all the intervening homogeneous coordinates are 0, and the last one is 1, then when you multiply all of this out with this thing, we'll get whatever mess we like in the first n coordinates, but the final coordinate is going to be, you'll get a -1 from this, but then you'll get a +1 from this, and so you'll get 0. But this is a point in the affine chart. So this gets sent to so we don't know what this is, but at the last coordinate we get a 0, which is a contradiction because this is supposed to be in the chart, and so this is supposed to be in the chart. Right, so what that tells us is that this last coordinate in fact must be 0, but then that means that all of the rest of them are 0 too, because without loss of generality there was no particular reason to pick this first one. So similarly, the remainder of the bottom row of t is 0. So we get that t is equal to b11 up to bn1, and then 0, 0, all up to 0, and then 1. Okay, and the point now is to see that this in fact is going to give us an affine transformation. So this should be 1, n plus 1. Right, well, let Q be any point in the affine chart. So this affine chart, we assume we're getting there by just letting the final coordinate be 1. And so we can take x1 up to xn. Applied to this, we are going to get the following. We will get, so you get the v, let's fill these in a bit more, bnn. So you get a matrix here, which is m, and that acts on the first n coordinates here. And then this last one just picks up the final column and then adds it on. And so what you're going to get, in fact, is an affine transformation where this last column gives you a translation. So perhaps that's Q is a bad letter. We'll let x be equal to that. Then Q can just be this final point, b1 n plus 1 up to bn n plus 1. Then t of x is equal to m on the vector x1 up to xn plus q. And you can see that that is indeed an affine transformation. Okay, so we're going to do just a final example here. So this will be example 514, and we'll look at a slightly more general case than what we were doing when we did an earlier thing for P1. We'll look at P2, and then we'll ask ourselves a question: when does a projective transformation given by a certain matrix, when is it actually a strictly rational transformation, and when is it affine? So suppose n is equal to 2 now, and let t be general So I'll stick with the notation in the notes. We'll go AX, AY, AZ, BX, BY, BZ, CX, CY, CZ. And let's apply it to the affine chart, which corresponds to the sort of last affine chart. So we'll assume that the last one is 1. So we have X, Y, Z goes to, so we're just multiplying this matrix by this and then just writing down what we get. So we're going to get AXX plus BYY plus CZ, AYY plus AZZ colon BXX plus BYY plus BZZ colon, and then the same thing with C. And so if we're assuming that Z here is 1, then so that means we divide, or Z's non-zero means we can divide through by Z, so we get, this turns into something that we can describe it as X over Z and Y over Z. So if U is X over Z and V is Y over Z, then you can see where this goes. You divide through by this final Z, and then clear Z's from the top and bottom, and you can see precisely where UV goes. So then so UV maps to, so we're taking this over this and then clearing the Z's to get AXU plus AYV plus AZ over CXU plus CYV plus CZ, and similarly for the other coordinates, so BXU plus BYV plus BZ over CXU plus CYV plus CZ. Okay, and then we want to know when this transformation is affine, and it's going to be affine precisely when when there are no values of U and V which make the bottom vanish, because then that will mean that this is still sent to a point of A2. So this is an affine transformation precisely when Cx equals Cy equals 0. Okay, and that finishes the end of this week's material.